Welcome everybody. In this fifth video of the series, we're going to fit the SIR epidemiological model that we've developed to the first 2 weeks of April. We'll then investigate the predictions that it makes for the next 6 weeks up to Memorial Day, May 25th. We'll discover that it does a pretty decent job of predicting what happens over those 6 weeks. We'll then fit the data from all of April up to Memorial Day and make a prediction for the future. We'll also include a way to predict the death rate from the infection rate, and ultimately we'll make a prediction for how the death toll increases over time, assuming that the model parameters remain unchanged by seasonal variation, changes in social distancing or testing, or any medical breakthroughs. Okay, so let's start by reminding you about where you can find the materials that we're going to talk about. They're at circle4.com/biophysics, and if you click on the free sample chapters link, that'll take you to the chapters page, and down here are the chapters. Remember, we have 1, 2, and 3, which kind of set up how to do all the stuff we've been doing. Here's the stuff for chapter 12. We're now up to version 3.8. Yes, there has been a little bit of mission creep on section 5. It now has a lot more stuff in it than I was thinking about, and we'll talk about that in the video. If you click on this link, you'll get the PDF, which I've already downloaded into my favorite PDF program. And so here it is. And we're going to start in section 12.5, which is now on page 47. So the first thing we want to talk about is how we're going to change the way that we fit the data, modeling it after the peak, which we know is when the infection rate is less than or equal to the recovery rate. All right, so I think the first question here is fairly straightforward. Just plug in equation 12.8, which is the equation for Ri, that it's Ki, which is the infection rate constant, times the number infectious, times the fraction susceptible. Then you need to compare that with the expression for the recovery rate, which is equation 1216, which is that the recovery rate is given by the recovery rate constant times the number infectious. Alright, so plugging in those two equations, we get into this inequality. We get this inequality, which says that this expression is always less than the recovery rate constant. Then we can do a little bit of algebra, and we can figure out that we can rewrite the change in the number infectious to be the change in the number infectious to be a constant, which we'll call the decay rate constant. And this decay rate constant is just the same as that expression. Alright, so here it is here. This is an important equation to remember. Then using this equation, we've got this calculus question, which kind of matches what we've done before. And you can show using calculus that it's given by this rather simple exponential decay equation. And then by doing a little bit of algebra, we can find that the infection rate is given by this expression, which can be simplified by collecting these terms into a single constant, which is what this equation is saying. And then we can find that by plugging this expression into equation 1266 and this expression into the same thing for the time, and then doing a little bit of algebra, we can find that the half-life for this exponential decay is given by this same expression, which is the same one that we first derived in chapter 4. Okay, and then there's some discussion about how exponential decay is different from exponential growth. And then question 1255 is a fairly straightforward algebra question, and these three equations that you can derive, I don't think I'll go through that because I think that's fairly straightforward, so hopefully you won't have any trouble with it. Then what we can do is we can download the spreadsheet for question 56. So let's do that now. After Excel loads, you need to click on Enable Editing, and we have a spreadsheet that once again has two tables. We've got the SIR model table here, and over here we have the data table, right, which has the number of infections per day in it. The parameter column, param dollars, right, remember we need dollar whenever we're talking about parameters in the algorithms, has the decay rate constant, the prefactor, Q, which is the thing that we're going to use to measure the goodness of fit, and when I click up here in the formula bar, it shows you what things are being calculated. So initially, we're just going to model from the 3rd of April up to the 14th of April. And in the handout, I kind of explained that I dropped the 2nd of April because it seemed to be in the transition period. And there's a research question for you to check that out if you're interested in seeing why. Now we're going to run Solver. It says in the handout, where are we? We want to run Solver, and we need to have the set objective to $J, $7, and we're going to set the to button to minimum, and we need to make the variable cells that we're going to change to be J3 and J5. So let's just do that. Alright, so we need to do Solver, which is under the Data tab. Click on Solver. Double check that everything's the way you want it to be. So J7, which is the cell for Q, we're minimizing, and we're changing J3, which is this guy, and J5, which is that guy. So if I click Solve, let's just move over so we can see the graph. At the moment it's not fitting very well, so we'll click Solve, and you'll see that the curve got better. I always like to do it at least twice, so we'll just hit Solver, do Solve again, and it looks like we've got a good fit. Okay, so the next part of the question asks you to make a copy and do a linear scale, so let's do that. So we've got the graph, hit Control C, click down here, hit Control V, makes a copy, and what we want to do is make the vertical axis a logarithmic, so double click on it, and there we go. And sorry, make it not logarithmic, so uncheck the logarithmic. So let's get rid of that so we can see the graph. So here's the graph on a linear scale. And then the next part of the question says add a trend line based on the data used in fit. So the way you do that is you click on here, and you need to right click on one of the orange dots, and we're going to add a trend line. And the instructions say to click on the trend line options, and you'll see there's a forecast thing here. What we want to do is forecast forward 41 periods, so type in 41, and then when you hit the X, it'll add the trend line. And so here you can see the dotted line that was added, and if you look at the graph, you'll see that the dotted line and the solid line from the exponential decay match up with each other actually very well during the days that we used, the first 2 weeks. Actually, it's a bit less than 2 weeks that we fitted the data to. The linear trend line stays like that. The exponential decay actually starts to go a little higher. Oh, and there's a comment in here that I forgot. When we do this, because we need to make this legend box just a little wider, so I'll make it a little wider still. There you go. If you make it wider, then you can actually see the linear trend line caption that Excel adds. Unfortunately, it doesn't rescale that box right now. Okay, so that's part C. And then in part D, I kind of confusingly ask you to do another linear trend line, and that's going to be to the USA data series, right, to this guy. And the reason for that, well, it's probably easiest just to show you why. So if I click on one of the blue dots and add a trend line, it'll be linear by default. So let's just get out of there so you can see it. And the blue dotted line, it's a little hard to see, but hopefully you can see that it actually matches up with the exponential decay model quite well over the whole period of that's in the graph, which is out to Memorial Day. That's what we did in part D. And it then asks you to talk about why, so let's just have a quick look. So the idea here is that the blue dotted line actually is a linear fit to the data, and it fits the data, pretty well because it looks pretty linear. And the fact that the exponential decay model actually, from the prediction, still fits on that line pretty well is a really good indication that what we're doing makes sense. Question 57 then asks you to fill in the SIR model table using equations 1272, and you'll notice the orders are slightly different, but it matches what's in the spreadsheet, and when you fill it in you'll kind of see why they go in that order. I think that's fairly straightforward. Part A is then once you've filled in that thing, this was actually what we did in the previous video. In part 4 we actually used this same algorithm, so this is really just a repeat, but it's really important that you understand it, so that's why I actually said do it again, because it'll help you. I'm not going to go through that in the video because you can go back and look at video 4 if you need a refresher on how to do that. So what I'm going to do now is open a spreadsheet that I prepared earlier. Okay, so here's the spreadsheet I prepared earlier. It has the mean infectious time of 16, and according to the instructions we're going to try using 8 and then 4 and then 2 and then 1. And if you use Control Z, you can go backwards through those, and if you look at the curve while you're hitting Control Z, you can get an idea about how the curve changes as we change the mean infectious time. So I got back to there using Control Z. Now if I hit Control Y, I can go back the other way and make the tau I smaller. If I hit Control Y, it gets smaller and smaller and smaller. Alright, and then Z again and go back up. Alright, so you should be able to make your own conclusions about what values of tau I seem to fit the data better. Question 1258 repeats a similar procedure, but this time we're mostly interested in what happens when you vary the population size n. At the beginning, don't forget to add a linear trend line based on the USA data, the blue dots. It'll help you see whether the fit's getting better or worse. So after completing question 58, you should have a good idea about how the population size and the mean infectious time affect the model. So figure 1217 is my summary of a reasonable fit, and you'll notice that the linear trend line, the black dotted line, matches up with the SIR model fairly well based on fitting to these first 2 weeks. What we haven't talked about so far is the fact that the long-term projection from the SIR model, the orange line in the curve, it looks promising that it's going down until you look at the time scale, which is pretty long, right? So 1 year is 52 weeks, which is way out here. So it's taken, according to the model, it's going to take a really long time for the infection rate to die out. In fact, longer than a year. Question 59 is similar to what we did in section 12.4, so I'll leave that as an exercise for you. One thing I would remind you of is that when you're running Solver, you should close all the other spreadsheets, and don't forget to clear out the SIR model table before you run Solver. If you don't, it'll take a really long time for it to come back. So you've been warned. So after doing all that, I came to the conclusion that a mean infectious time of around 8 days seems to be a good choice, and that the model population size should be about 1/2 of the US total population. This value of 8 days actually matches up with an SIR model that was used to model Chinese data and published in the journal Science. So question 60 I think is fairly straightforward, so I'll leave that as an exercise for you. The last part's kind of important for what we'll do next, because it gets you to compare using a time step of 1/10 of a day with using a time step of 1 day. And what you should discover is that increasing the time step for this period in time really doesn't make much of a difference to the model, which allows us then to use the least squares fit to the SIR model, which is what we're going to talk about now. If we click on this link, we'll open a spreadsheet, and when it opens, you need to click on Enable Editing so that you can change the cells. And you'll notice that we have in our param dollar column, we have a whole bunch of parameters that should be fairly familiar now. And I've got the mean infectious time at 16 days and the model population size at 33 million, which is probably a bit low. But let's see what we can do with Solver. So to populate the table, we need to input the formula for the residuals, right? Column R. Oh, let me just explain. This column is the same stuff that was over here in the new infections data table, but now because the time step matches, we can transfer those numbers into the SIR model table, and so that's infections per day. And what we need in this column are the residuals, and so the formula for that is that it's the observed value, which is the value reported by the European CDC, minus the expected value from the SIR model, which is in column E. So that's the formula for the residuals, and then R squared is just the square of the residuals, so it's equal to this residuals times the residual. And then those two things need to be copied down until we run out of data, which is always go too far. Where is it? There it goes. Alright, so now we've filled in the residuals, and once we've got the square of the residuals, we can check to see what Q is doing, right, the quality of fit. And so it's the sum, and the blue box should be, yes, all the values of R squared. Okay, so now we can run Solver, and if I just click there, don't have to click there, but I always like to. Then if you click on Data, and you'll get Solver way over here on the right, and if you click on Solver, let's just double check that it's doing what we want. A19 is the cell with Q, which is what we want. We want the objective to be a minimum because we want to minimize Q, and we want to do that by changing A3, which is our model population size. So now when we hit solve, Excel is going to adjust the value of n and find the value of n that makes Q the smallest. And it's kind of interesting, right? Because the spreadsheet now is actually calculating everything on the fly. So let's see how that goes. All right, so didn't take too long. And you'll notice that the orange line now matches up with the dotted line really quite well. So let's just run Solver again. I always like to do it at least twice. Okay, and we've got the message that we have all the optimality conditions satisfied, so that's good. And let's look at what we got. So the mean infectious time was 16, and it pushed the model population size up to about 225 million, which is, you know, getting up to what, about 2/3 of the actual US population, which seems like a reasonable number. So that's actually really good. Part C asks you to change the fit to instead of adjusting the model population size, instead adjust the mean infectious time. I'll leave that as an exercise for you, but I'd like to show you just how to do Part E, just in case that gives you any trouble. So Part E says we need to do Solver, so click on the Data tab, click on Solver. We are again going to be finding the minimum of Q. We might check that's a minimum. Now what we want to do is, instead of just doing n, we want to do both of them. So I'm going to highlight that just by left click dragging across it, and then click on here, and then hold down Control or Command on a Mac, and then click on Tau I. So what this will do is Excel will now adjust both things and see if it can find the lowest value of Q. So let's click Solve and see how that works. At the bottom of the screen, I don't think you'll be able to see it from my screen because it's just off the region that's in the video, but it's showing how many iterations, and it's talking about how Q was changing, and you'll notice it changed very, very, very slightly. And if you click OK, you'll see that the parameter values that we got are kind of crazy, right? The tau I is now 1/100th of a day, so a person's only infectious for 1/100th of a day, which is clearly not reasonable. And it also says that the model population is like, what is that? Wow, that's a big number, right? That's 100 times bigger than the actual population of the US, actually more than that. So those two numbers really don't make any sense. And the reason why is that what Solver was trying to do was to adjust this orange curve and make it match up with the data as well as it could. And seeing the linear fit is actually all, doing a pretty good job. You can see that adjusting these two things together allows you to do kind of crazy things, which is why I think the approach we were doing before is actually better because it's much easier to understand what's happening. But I wanted to show you this idea that Excel can actually do a full-blown, well, in this case, only two of the parameters, but you can also do 3 and then 4. So that's what the rest of question 59 is about. So it's really a cautionary tale. If you're using one of these automated least squares fits programs, if you have a lot of adjustable parameters, it'll just find the value that makes the thing that you're trying to minimize, Q, as low as possible. And it doesn't care whether they make sense or not. So in the handout, I kind of talk about that. Where are we? Here we go, in this yellow box. And kind of go, well, to me it seems like this is a pretty good value for N, right, about the full population, and that tau I being 8 also seems like a fairly reasonable number. But, these two things, you can adjust both of them together and keep the fit pretty much the same. And the idea is that the USA data doesn't have enough structure to determine all of the SIR parameter models, so it underspecifies the data. Also, the SIR model, or you could say this the other way around, that the SIR model overspecifies the data that we have. Again, the idea is the data look like a straight line, and so, the equation for a straight line has 2 parameters, the slope and the intercept, and so you really only need 2 parameters to describe this straight line. Okay, so now that we have a good handle on how to model the infection rate, let's talk about how we can use what we've learned to model the death rate. Now, the SIR model does not explicitly model the death of infected individuals, right? So we need to come up with a way to connect the infection rate to the mortality rate, right? The rate that people die, which is also reported by the European CDC. So the idea is that we're going to have a fixed fraction, which we're going to call the mortality ratio, which is the number of people who get infected who die, and that's based on the reported numbers. The other thing in this equation that we're going to use is, so here's the scaling factor, right? And there's this mortality delay time, which is a time shift. It says that when you're comparing the death rate with the infection rate, there's going to be a time shift, right? And that time shift is the number of days it takes from somebody being reported to be infectious to when they eventually die, right, if that was their fate. So the idea is that we're going to use a progress table, just like we did in Chapter 6 for oxygen binding to myoglobin. And to do that, we need to click on this spreadsheet, click Enable Editing, and let's just go through the spreadsheet to make sure that we understand what it has in it. So let's just talk about the table first. So we have a USA data table, so here it is, and it's got data from the European CDC. I've got date and then day, counting the 26th of February as day 0. And then we have here the 2 columns, one for the infection rate and one for the mortality rate. And columns G is the expected value based on the equation that we were just talking about. So if I click in here, you'll see that what it's doing is it's calculating using that formula. It says that this value is MR, right, in cell A3, times the value of the infection rate, in this case 1, 2, 3, 4 days earlier. So that's how the equation is implemented in Excel. And then here we're doing residuals, and so residuals again are the observed value, which is 2, subtracted, and then you subtract the expected value. And the reason that I started the expected values down here is just because you need some non-zero numbers to be able to make a comparison. So that was the residual, and then the square of the residual, and that goes all the way down to the end of the period that we're going to consider. And it turns out we're only going to go out to April 12th because that was the end of the transition period. So the curve goes up like this, and then it started just leveling out. So that's why I picked that time for the data. The blue series is the actual data, right? USA deaths. And the orange curve here is the one that comes from the expected curve, right, from the equation we were just talking about. And what I asked you to do was just to adjust. So I'm going to just move this so we can see it. I'll put it here. If you adjust this thing, 0.03, which would be 3%, if I make it 0.04, you'll see the orange dots move up. And if I make it 0.05, they get closer. And actually that doesn't look too bad. And then the idea is that we want to run solver. So again, click on the data tab, click on solver, check that it's actually doing what you want. So let's have a look. The objective is Q, which is what we want. We're finding the minimum, and we're adjusting A3, which is MR. So let's do that. And I usually do it twice. All right. Oop. Let's get rid of that spreadsheet because I don't need that. All right. It's actually a good point. Whenever you're running solver, make sure you've only got one spreadsheet open, because we were actually recalculating both spreadsheets. I'm not quite sure why Excel does that, but it can really mess you up if you have one of our really long spreadsheets with 1,000 rows in it, because it just makes everything go really slow. Anyway, so here are the things that you need to do. So to fill in our progress table, we need to copy this value of MR. So I'm going to do Control C, and again on a Mac it's Command C, and then Control V, and it pastes because it's just a number. But Q is a formula, so if you do Control C and then put it over here, do Control V, we need to paste it as a number. So you'll see this thing came up, and I'm going to click on here, values. And so what that did was it actually put the value of Q there, and you'll notice that it gets automatically plotted in our progress table graph. All right, so, and then let's try, let me skip the 5-day one. Let me move this out of the way again. Let's change this one. It was 4 days. I'll move it up, and I'll skip 5 and do 6. So if I move it up 1, that would be 5 days, and there's 6. So let's do that. And then you need to left double click to fill in the rest of the table. Don't forget to do that. And then if we run solver again, so click on data, hit solver, and just double check that things are what you want, hit solve, and so that worked. Let me do it one more time. Alright, and then copy, I can copy MR, the mortality ratio. Remember we were doing 6 days, and then the Q value, Control C, Control V, and then we want to make it do paste values, and you'll notice that the value goes down quite a lot. I think once you've seen that, the idea behind this question, question 63, I think is fairly straightforward. And question 64, which is after that, I think that one, yeah, that one's actually also fairly straightforward. So I'll leave that for you. Then there's a statistics question. So if you've got statistics, you can come up with a test to see whether the correlation is correct. And then in the yellow box I show my answer, and so when I did the fit, I got the lowest 4 were here, and you can see the minimum is somewhere between 6 and 7 days. 6 is just slightly lower than 7. And if you put this, both of them, the scaled thing, right? So that's our equation 1275 that we talked about, on the same graph, you'll notice that the blue circles, open circles, the death rate, and the orange dots are the scaled infection rate. So it's kind of showing that if you know the orange dots, you can make a reasonable prediction for what happens for the blue circles. Okay. Oh, and the next graph is just kind of an interesting one. If I was started writing this chapter after I'd had all this data, I probably would have started with this graph. So this is just a really simple raw plotting of the data on a semi-log graph. And I'm not doing anything fancy. I'm just doing this line here is just an Excel exponential trend line, and so is the dotted black line as well, dashed black line. And you can see that the growth period is an exponential growth, and then after social distancing took effect, we get an exponential decay. So that's why I called it that. And if you're interested, you should go through. Well, you should go through and read that stuff. The next topic that I wanted to talk about is something that came up in the media a little while ago, and I thought it would be interesting to see what we could figure out about what would happen if social distancing had been implemented earlier. And in our case, I'm just going to do 1 week. Okay, it's just 7 days. Now, because of this fit, we can actually do something pretty straightforward. It's basically just data analysis. This is an exponential decay, and this is an exponential growth. This point here is the crossover between growth and exponential decay. And the idea is that our exponential growth can be given by this equation. And so there's a prefactor and then our growth rate constant, which we actually did talk about what that meant before. And so the idea is that if you just do a time shift of 7 days, you can keep on this exponential growth, and what you do is you change the time that you get off the exponential growth. So if you shift 7 days down here, you can have this thing go like this and have a curve that's lower because you started social distancing earlier. The slope, this decay slope, doesn't depend on how many there are, at least to a good first order approximation. And we can also try to fit the in-between time, this transition time, also with an exponential function. So in here I kind of go through how to do that. This is the curve that you get, and here I didn't do Excel's trend line, I actually did a least squares fit, so that's why it fits the last data here quite well. And you can kind of see that what it's doing is you can see that this distance here is about 7 days, so that's the 7 day earlier thing. And then this transition line, you can see here it is here, that's also been shifted 1, 2, 3, 4, 5, 6, 7 days down, right? So our procedure worked fairly well. And so this is the transition that's the same shape as that one. And of course we stayed on the exponential growth here, and you'll see this is about 7 days earlier as well. So on a semi-log plot, that doesn't look all that super dramatic, but semi-log plots, log plots of any kind of under emphasize big changes. So here that's the same thing on a linear scale, and you can see the difference between this purple line and the green and gray line is actually the number of people who were saved per day, right? So it's not just the number that happened when social distancing first started. Every day since then, that delay of 7 days has been adding tens of thousands of people getting infected per day because of the 7 day delay. And the purpose of that I'm bringing this up is that that's a public health policy lesson, right? This is looking forward. If we have something like this happen again, it's really important to know that acting early, particularly during this exponential growth period, is just super important. Because of that, I decided to show the numbers here in tabular form. So here's the actual data from the European CDC. Here's the empirical fit just to see how well it does, and it's really pretty good, right? These two numbers are pretty much exactly the same. And then if we did it 7 days earlier, this is the number of infections by Memorial Day, right, May 25th. And the number of people who were saved from infections is about 1.4 million. And the number of people who could have been saved from dying from COVID-19 is quite remarkable, right? It's 82,000 people. So I left as a research question redoing that empirical fit with the full-blown SIR model. I think that would be an interesting exercise to see if you get something consistent or whether it's different or not. The next topic is in question 68, which is talking about something that some politicians have said. They've made claims that the infection rate in their region was either staying the same or going up, basically just because of increased testing, right? Which I think is implying that more mild or asymptomatic cases are being detected because of the increased testing. So the question is, let's fact check those politicians and see if we can figure it out. And so question part C actually asks you to, B asks you to do that, and then C asks you to record a specific thing. One of the things that I just wanted to talk about in the video a little bit is that on March 6th, the World Health Organization reported a thing that they called the crude mortality ratio, which is just total number of deaths divided by reported cases. And they said that the numbers that they had were between 3 and 4%. So that number's comparable to, but not exactly the same as, the mortality ratio that we had in our equation. In fact, if you calculate the crude mortality ratio for the data that we have for the USA, you end up getting a value of around 6%, which is significantly higher, right? And so that's kind of troubling. And also the yellow box here, I actually talk about sort of a very straightforward way of trying to investigate the claim. And so here's the mortality ratio calculated using our equation as a function of time. And the blue dots are daily values, and the orange open squares are weekly averages. So the average goes, over this range, right? So the box is in the middle of the period that it's averaging, not at the end. All right, and you can see that there's a steady decline in the mortality ratio over the 4 weeks prior to Memorial Day, and the trend does look like it's heading towards the range here that the WHO had of 0.03 right to 0.04, which is between 3 and 4%. So you can see there are already a couple of dots that are down there, and the trend is that it's going towards that. The issue that you hopefully will realize is that this causes a problem for predicting the death toll, because as the mortality ratio goes down, the number of infections that we're modeling, calculating the mortality rate from that becomes more and more tricky, because if this thing's changing, we've got kind of a moving target. The next section is actually making those projections. So let's download this spreadsheet and make sure that we understand what's in it. Okay, so once you get the spreadsheet, you should click on Enable Editing, and let's just check this cell here. It's formatted in the what Excel calls the input style. So let's show you where that came, right? So here, input style. The formula is that it's just equal to the value over here in our data table. So that's kind of an input, and I thought rather than making it a parameter, just labeling it with the input style was a good idea. Now equation 1277 says that the value underneath that, the new value of IT, should be the old value plus the infection rate, which is that guy, the new infection rate, times delta T, which is over here, and because it's in our param dollar column, we need to hit F4 and get dollars. Alright, so there we go, and we can then copy that down And then the RM column starts here, and I've put in the first formula for you, and it's using our 6-day delay, and it's saying that equals to MR times the infection rate, so that's good. And then this guy should be given by equation 1278, which is equal to DT, which again is in an input box because we got it from over here in the European CDC data table. So it's equal to the old one plus RM, which we just calculated, times delta T, which is over here, the time step. Hit F4, hit enter, and then we can highlight both of those by left click dragging through the middle, and then do our left double click, go from an open cross to a closed cross, left double click, and it should populate the whole spreadsheet. So down here we have graphs, right? So these graphs are our best fit estimates. Oh, I forgot to tell you, right? We're using a mean infectious time of 8, and we're using a model population of half the total US population. All right, here we have the USA infections, and I did them as tiny wee little black dots. They fall pretty much exactly on top of the orange curve, which is the SIR model. So that's kind of satisfying. The thing that isn't satisfying is that because of the shape of the curve, not only does it take a long time for it to kind of flatten out to zero growth, but we get up to nearly 4 million confirmed infections by that end of that time. And then even more alarming is the death toll. Right, so this is the cumulative confirmed deaths, and you'll see that the black dots, which we had to calculate using a value of MR, and we chose the value that we got from the initial growth period, you'll see that it fits quite well at the beginning, and then it goes a bit high, and then it's starting to turn back towards the orange curve. So that's the prediction, and again, this is kind of alarming because the numbers are so big. Right, we're already up to 100,000, and it predicts that we get to about 200,000 here on before day 200. The other thing that I just wanted to quickly show you was the idea about changing this axes scales. So if I left double click on here, let's change the maximum. So I'm going to make sure that you find the axis options, click on this bar thing, change this to 60 days, and then we can do the same thing with the vertical axis and change that to, let's try 2 million. So 2 million is 2E6. All right, so you can see the black dots a little better, and you can see they're really the SIR model is the smooth curve, and the dots are just tracking right along. For the other curve, we need to do the same, and you'll see that because of the uncertainty in the mortality ratio, it works quite well here at the beginning, but then there was a period where the mortality ratio was actually bigger than 6%, and you can see it's kind of trending back down towards the orange curve, and only time will tell what happens with this. In the chapter, after the question, I kind of go through what my answers for that were. So here's the infection toll data, and I put in upper and lower bounds based on what I thought were reasonable ranges for the values. And I also put in some dotted lines to indicate milestones. So the 2 million infections should happen around June 13th, and 3 million infections around August 28th. If the model stays accurate, which assumes that all the parameters stay the same. The death toll has a bigger range of uncertainty, primarily because of the fact that we need to put in the mortality ratio. And as we talked about before, that mortality ratio, the orange curve is using the value of around 6%. But as we noticed during May up to Memorial Day, that number for the mortality ratio was trending down towards the range that the WHO had found earlier on. And so this bottom dashed line actually is using a mortality ratio of the low end of the WHO range of 3%. And the upper value is using what I actually did was kind of tricky. In question E, I got asked you to sample various values, and then I actually went through a procedure that it makes the dashed curve, this top dash curve, actually goes through that last data point. Then after that, I have a bunch of research questions, which are intended to be projects for students to work on. And then at the end here, seeing we're actually making predictions about pretty serious things, I wanted to just talk about the kind of modeling that we're doing. I think the model that we're doing is very easy to understand, and so we know it's not going to be perfect. And this is just a cautionary tale. It's kind of an interesting quote. So John von Neumann, who was a very famous computer science guy, said quite famously, with 4 parameters I can fit an elephant, here's the elephant, and with 5 parameters I can make him wiggle his trunk. Right? So it's really saying don't use any more parameters than you need, because you can do all kinds of crazy things when you add more parameters. And as we already noticed, the SIR model is already overspecified and has too many parameters for the data that we're analyzing. Now, if you have more data, and there are plenty of other data that you can use and input into these models, then you can justify using more parameters. Oh, and then my last little thing, right? These simple models, the advantage of simple models is that they're simple, right? And we don't use any fudge factors to try to make it work better. We only put in things that seem to be the absolute minimum. And again, the idea is that we're not actually really trying to predict the total death toll in America. This is just a simple idea to give you an idea of where we're going. And so the analogy that I came up with is we're not trying to predict tomorrow's weather, we're just trying to understand why clouds form in layers. Getting back to PowerPoint, here's the graph that we were just talking about, predicting the death toll. I'd just like to remind you about where everything is for this project. It's at circle4.com/biophysics, and if you go to the top of the page, you can find the links for the chapters and the videos.